Okay, quadratic versus linear. If you're looking at a table, your first move is to look at the change. See how fast it's changing. So -4 to a -7 to a -10 to a -13. Looks like it's getting smaller and smaller. So it's going down. That's negative, and it's going down 3 every time that this side goes up 1. So when your x's increase by 1, your y's decrease by 3. So how much is it changing every single time? It's going down 3. So your change is a -3. So here's how you start your rule. Well, I guess before we start the rule, this is the one that we love because it is linear. Now linear means exactly that. Linear means it changes at a constant rate. So every time it's changing the same rate. Down 3, down 3, down 3, down 3, down 3. I guess the y is because changes at a constant rate. Alright, so that's why it's linear. Okay, now to come up with the rule, come up with the function, it is always going to be times by a -3. And now let's just pick one of those pairs, let's test them, let's see where we get to. I'm going to try 4. Okay, 4 gives you a -10. You start with 4 and you end up at -10. So if I try my rule out, if I do 4 times by a -3, I'm ending up at -12. And I need to end up at -10, so here's what I'm going to do. I'm going to times by 3, then add 2. Because I know a -12 plus 2 is going to end me up where I want to at -10. So let's test another pair. Let's test 6. 6 times -3 equals -18 plus 2 is 16. -16. And that's where I need to end up. So I'm solid. I feel pretty comfortable. I hand it in and move on. This pattern right here, 2 to a 7, that changed 5 times. 7 to a 14, that changed 7 times. 14 to a 23, that went up 9. This went up 11. I think you see the pattern. So plus 5 plus 7 plus 9 plus 11 plus 13, it's increasing every time. But it's increasing every time by the same amount. Always you just add 2 more. So this is the definition of a quadratic. This guy right here is quadratic. And a quadratic, here's how I know it's quadratic. Because the second change is constant. I am looking for when it is always changing at the same rate. And on a quadratic, it's not until you look at the second change that it's constant. So your first changed by 5, then by 7, then by 9, then by 11, then by 13. And these are kind of the same. They just went up 1 every time. Okay, now the rule on this one. Because it is a quadratic, here's what you know. Quadratic, there is going to be a square. The exponent is going to be 2. And I'm going to give you super easy quadratic because we haven't done them. So, but look at this. This is going to be a piece of cake. You know this so far. You know it's a quadratic because the second change is constant. And you have to know a quadratic means this. Means the exponent is 2. So let's look at 4 and let's see if we can figure out how 4 is ending up at a 14. So I'm going to do square the number, because I know a square has to come in sooner or later. So square the number So if I choose 4, I'm going to do 4 squared. 4 squared gives me a 16. I need to end up with 14. Square the number, then minus 2. Because 16 I wanted to minus 2 because I want to end up at 14. Now, that's just a suspicion. It's got to be proven with a few more pairs. So let's try 5. 5 squared is 25. And sure enough, 25 minus 2 gives me my target, 23. One more for good measure. Let's try 6. 6 squared, that's going to give you a 36, and a 36 subtract 2 ends you up at 34. So, pretty sweet. Not too bad. Okay, now if you're looking at these guys and you're trying to figure out the patterns and which one is linear and which one is quadratic, let's dig in. So this first one, 8 to 12, that went up 4. 2 to 4, that went up 2. So if you're asking yourself, how do you know if that's quadratic or if that's linear? Hopefully you have a good argument, but you end up with this. There is absolutely not enough data. So you have no idea. I know that this added 4 when this added 2, but I don't know what happened next. I need at least 3 pairs. All they give me is 2. And I can't do anything with 2 because I don't know what they're going to add next. I don't know if they're going to add 7 or 4 or 20, who knows. So to determine a pattern, you have to have at least 3 pairs. So if they give you 2, who knows? Not enough data on either one of them. Okay, draw a sequence of pictures that increases at a linear rate. Okay, a linear rate, that is x to the 1, that is the first dimension. So, picture 1, I'm going to have 1 cube. Picture 2, so it looks like that. Picture 3 looks like this. Picture 4 looks like this. Just make it easy. So it looks like I'm collecting a tower of cubes. Now what happens from picture to picture? I just add 1 cube. So pretty slick. The change is plus 1 cube each time. It's linear because you're adding this constant amount every time. Okay, now let's do the same thing, but let's look at a quadratic. Okay, quadratic is x squared. That is the second dimension. That means you're going to grow in width as well as height. So picture 1, there we go. Picture 2 though, you're going to have 4 cubes. Picture 3, you're going to have 9 cubes. Picture 4, you are going to have 16. So this is simply a 4 by 4. This is a 3 by 3. This is a 2 by 2. This is a 1 by 1. So your picture is growing, it's getting taller, but it's also getting wider. And that is the definition of a quadratic. You're changing in 2 dimensions. Suppose you invest into a bank account or something and your money grows at a linear rate. So a table, this is going to be month, this is going to be your money. So month 1, let's say you've got $100. Month 2, you got $200. Month 3, you got $300. Month 4, you got $400. So it changes $100 every month. That's linear. So it's constant, it's dependable, same rate every month. Now if you're looking at a quadratic, maybe month 1 you have $100, maybe month 2 you have $200. So far the same. But now what happens in month 3, you're not gonna have 300 bucks, you're gonna have 400 bucks. Maybe at month 4, you're gonna have 700 bucks, and at month 5, let's see how much you're gonna have. Are you gonna have 1100 bucks? So there's totally a pattern going on. I'm adding 100 bucks, but now on this time I'm adding 200 bucks. From here to here I add 300 bucks. From here to here I add 400 bucks. So I'm adding more and more each time. But if I look at the second change, that's going up by 100 every time. So there's your quadratic. Okay, is this a linear sequence or a quadratic sequence? Maybe let's put it into a table. So this is the figure and this is the cubes. Organize it into a table. Now figure 1, I'm going to count the cubes, and I count 2, 4, 6, 8, 10, 12, 14 cubes. Figure 2 is, what is that, 3 by 4, that's 12. That's 12, so I'm 24, I'm at 26. Figure 3, I know there's 20 cubes in there, 20 in there, so I'm at 42. Okay, now all you really need is 3. You have to have a minimum of 3 and you can find the pattern. 14 to 26, how much did that change? That just went up 12. Okay, what about 42 to 26? That went up 16. So you can probably totally guess number 4. I'll bet you money it is going to go up 20. So 42 plus 20 is going to be 62 cubes. I know that because these are increasing by 4 every time. So, is that linear or is that quadratic? The answer is quadratic, but why? Because, whoops, your second change is constant. So it's increasing at a constant rate. Alright. What about this guy? Same thing, let's do this. This is figure and this is the cubes. So figure 1 is going to be 3 cubes, figure 2 is going to be 5 cubes, figure 3 is going to be 7. Done. You got a pattern. Total easy pattern. It's going up 2 cubes every time. So this one is linear because it changes at a constant rate. Now, here's the rule. You always times by your change. I'm going to times by 2. So let's test it. 2 times by 2 is a 4, but I need to end up with 5, so I'm going to then plus 1. So let's check another one. 3 times 2 is 6. 6 plus 1 is 7. Awesome. I started at 3, ended at 7. That's where I've got to be. Done. So my rule is y equals 3x. No, not 3x. 2x. I times by 2, then plus 1. Alright, write the function that explains what is going on. So let's examine the change. 2 to 8, that went up 6. 8 to 18, that went up 10. 18 to 32, went up 14. That went up 18. Okay, this is changing only by 1 every time. So here's what's got to go off in your head. You know what? This sucker is a quadratic. So if it is a quadratic, there has to be an x squared. Has to be a square. So let's start off with our rule. And let's say, you know what? Square the number. That's our first move. Okay, let's look 4. I'm going to plug 4 into my rule. So I'm going to first square the number. So I'm going to go 4 squared, and I am at 16. Somehow I need to end up at 32. So you think about how 16 is going to end up at 32. And maybe not much is jumping out. But so let's check another one. Let's check 3. Alright, 3 squared is a 9. But somehow I've got to end up at 18. 16 has to end up at 32. And now you're thinking, you know what? 9 times 2 equals 18. 16 times 2 equals 32. So maybe here's my rule. Maybe I square the number, then times by 2. Let's try one more. 2. Alright, 2 squared is 4. 4 times 2 is 8. Okay, that's it. So my rule is going to be square the number and times by 2. Y equals 2x squared. Okay, this guy over here, let's have a look at this one. Negative 2 to negative 1, that's going up 1. Negative 1 to 0, that's going up 1. 0 to 1, that's up 1. 1 to 2. Alright, up 1 every time. But that's a trick question. It's not 1 up every time. This goes up 1 every time. This goes up 4. So when your x's go up 4 times, your y's only go up once. What is the change? You made $1, but you had to work for 4 hours. So your change is always your y's divided by your x's. 1 divided by 4 is 0.25. You made 25 cents an hour. So your change is 1/4. So here's your rule. You're going to times by 1/4. And that actually is the same thing as dividing by 4. So let's test the number. Let's test 8. 8 divided by 4 is 2. Okay, now 8 has to end up at negative 1. So 2 subtract 3 equals negative 1. Okay, let's try one more. Let's try 12. So here's my rule. I'm going to do 12 divided by 4. That's 3. And then I'm going to subtract 3, and that ends up as 0. Okay, I lock it in. I feel pretty good. That is it. So my rule is y equals x divided by 4 subtract 3. Alright, let's do a couple of these, and then I think we're going to have to cut it in half, do part 2. Here we go. Multiply, so you're going to multiply what's on the outside, which is a 2 and a 1, together. So 2 times 1 is 2, and then you're going to multiply what's underneath together. 20 times 15, that's 300, and x cubed times x to the 1 is x to the 3 plus 1, so it's x to the 4. Okay, now here's your golden rule. Anytime you've got a number underneath the radical, let's break it up to its prime factors. That's going to be 103, 10 and 10, 5 and 2, 5 and 2. So, here we go. You're going to have 2 times the square root of 5 squared times 2 squared times 3 times x to the 4. Okay, now let's start pulling stuff out. Let's pull out in sets of 2. On the outside I got a 2. Anything that comes out, I multiply it. I'm going to pull out a 5. I'm going to pull out a 2. The 3 stays put. And I'm going to pull out x squared, because there's 2 sets of 2 and 4. So multiply all your terms on the outside. I got 2, 5, and a 2. That's a 20 x squared on the outside. Underneath is just your 3. Okay, the next one, it looks pretty good, except for it's illegal. Anytime that you have a fraction, it is illegal to have in the denominator a radical. So that square root of 2's bad news. Now, because it's a fraction, you can simplify it just like you would a normal fraction. So anything on the outside, your 4 and 5, you ask yourself, can I clean those up? 4 and 5, do they have anything in common? The answer is no. But you can also do your insides. 5 and 2, same problem. They're simplified as far as they go. So now you got to multiply this by a 1. You're going to multiply it by the denominator. Let's look at the denominator, and here's your problem right here. That is what is illegal. So I'm just going to copy and paste that on the top and the bottom. I don't need the 5, I just need the square root of 2. Alright. So when I multiply my tops, I'm going to get, I can times the 5 and 2 together since they're both underneath radicals. So I'm going to have 4 times the square root of 10. And then on the bottom, you're going to have 5 times the square root of 4. There's the genius thing that you just did. You just created purposefully a perfect square. Anytime you have a square root times itself, you're going to create a perfect square. The square root of 4 is really a 2. So you have 5 times 2, which is just 10. Now you're looking at that, and that looks a lot better. You're feeling pretty good. But 4/10, they're both on outside, so you can simplify 4/10. Your best and final answer is 2 times the square root of 10 divided by 5. This is what you take home and hand in to mama.